Hello and welcome once again for another video, and this one is going to be another example problem, the second example problem for day 2. An object of mass 10 kilograms initially at rest experiences a horizontal acceleration, a constant horizontal acceleration of 4 meters per second squared due to the action of a resultant force applied for 20 seconds, and we want to determine the amount of energy transfer by work in kilojoules. So we should note again that work is equal to the integral of f dot ds, where f is obviously a vector, ds is also a vector. And so there's different ways that we can approach this. A common thing that we're going to find is that this is going to be, it's not going to be in this particular problem, but a common thing that we're going to find is that this is going to be equal to the pressure as a function of the volume times the an element of the volume, dV, okay? Not in this case, though. In this case, what we have is we have a force rather than trying to convert everything to pressure and volume. We have a force that's acting through some displacement. Now, the nice thing is that we can choose a reference frame. So you should remember your physics, your physics 1 and 2, mostly physics 1 here. So what I'm going to do is I'm going to say x1, which is x at the initial time, is going to be equal to 0 meters. That's my reference frame. And since this is only acting in the horizontal direction, I'm going to have some x2 here. And at the moment, I don't know what that is, but we'll use some facts to get x2. So now let's take that's going to give us the distance. So in this case, for us, the integral of f dot ds is going to be equal to, well, note that this is something you should remember from calculus. F dot ds is going to be equal to the magnitude of the force, F, times the magnitude of the little element of distance, displacement here, times the cosine of the angle between the two of them. But in this case, because we have a constant horizontal acceleration, and the force is obviously going to be all horizontal, and the distance is also going to be all horizontal, the ds. The cosine of the angle between those two is going to be 1, because either they're facing in the exact same direction, the force, and in this case they are, because it starts off initially at rest. And so the only thing that we can say is that the force must be pushing it in that direction, because it started initially at rest, and the only way for it to then move is by this force. So the force must be in the exact same direction, rather than being 180 degrees in the opposite direction, right? Which would then give us a -1 for the cosine. Cosine of 180 degrees is -1. But in this case, the angle between these two things, the force and the displacement vectors, is 0 degrees. They're exactly perfectly parallel. And that means that the cosine of that is going to be, cosine of 0 is just plain 1. So that means that this is just going to be the magnitude of the force times the magnitude of the ds vector here. And since I'm using x, I'm going to replace that with dx. So the magnitude of ds in this case is going to be dx, a little element down here. Okay, so that's my dx. So that means that my integral then, work, is going to be equal to, now the magnitude of the force, which is going to be a constant in this case, that's because the constant horizontal acceleration, and that we also don't have a changing mass, it's just a constant mass as well, means that this is going to be, the force is going to be constant over that period of time. So I can pull that out of the integral times dx from x1 to x2. Now we already know what x1 is, that's 0, and x2 is something that we're going to have to determine, which we will do in a moment. Okay, so now let's take note of what we know. We know that m is equal to 10 kilograms. That was given to us. We know that a constant acceleration a, which I'll call c, is 4 meters per second squared, and we'll see why I call this c in a moment. And we also know that the time t is going to be 20 seconds. All of these are going to be important for us, as we'll see in a moment. Now, the nice thing is that if we have a constant acceleration, remember that velocity v, which your book uses a capital V for here, is dx dt, right? If I have nice straight line motion like I have here, and the other thing is that the acceleration a is equal to dx squared, d squared x, sorry. I did the notation bad there. dt squared, that would be our acceleration. And in this case, my x of t is just going, my dx, my d squared x, d squared x dt is just equal to a constant c, dt squared. And the reason that's going to be important is then when we want to determine the distance that's traveled, remember from physics 1, you have these kinematic equations. Well, the kinematic equations can be nicely derived. So in this case, if I were to integrate this with respect to t, dt here, and this side, I can pull the constant out of that integral. Then what I get is I get dx dt is going to be equal to c times t, right? If I go from t1 to t2, I'm not going to do that. I'm just going to leave this as an improper integral here, or as I'm just going to leave this in this format for a moment. And then I integrate again dx dt with respect to t. What I'm going to find is, this is a way that we can derive these kinematic equations, right? There's no velocity, by the way. Dx dt is literally, the velocity is only going to come from that acceleration. There was no initial velocity that I had to add in, right? So because there was no initial velocity, this is going to work out perfectly fine. And what I'm going to find is that x of t here is going to be equal to c t squared over 2. So that will actually give me my second part, right, my x of t. By choosing this reference frame, this made everything very convenient. I should have added in a constant here, but the constant actually is going to go away because of how I chose my reference frame. So this is convenient, right? There should have been a plus c over here because I wasn't going from x1 to x2 or whatever. And so now what I can do is I can figure out what the value is at t equal to 20. So x of 20 is going to be equal to c times 20 squared all divided by 2. And C was equal to 4, right? We already mentioned that C was equal to 4 meters per second squared here. And the units here are going to be 20 seconds, so it's going to be seconds squared. The whole thing should be squared. So this is going to be equal to 4 meters per second squared times 400 seconds squared divided by 2, which is equal to 800 meters. So x2 is going to be this. So x2 then is equal to 800 meters. Great, so now we actually have x2 here that we can use for our integral. Now the other thing is we need to find this magnitude of the force. And the magnitude of the force, well, in this case, the magnitude of the force is going to be equal to m times that constant acceleration c that I was having. So this is going to be equal to 10 kilograms, right? That was my mass up here. 10 kilograms times the constant acceleration, which was 4 meters per second squared. And this is going to come out in terms of newtons. So this ends up being 40 newtons because a kilogram meter per second squared is a newton. Okay? We'll just make note of that. I did the conversion already. Maybe I should have walked through the conversion, but I think at this point you get the idea. Okay, so that means that my work done then must be equal to that magnitude of the force, which is 40 newtons, times the integral of from x1 to x2 dx, which is obviously a very simple integral, so that's equal to 40 newtons times x2 minus x1. Well, x1 is 0, so that's simple, and x2 is 800 meters, so 800 minus 0, this is going to be 40 newtons times 800 meters, which is equal to 32,000 Newton times meter, which is the same 1 Newton times meter is equal to 1 joule. So that means this is equal to 32,000 joules. However, if we go back to the problem, it said determine the total amount of energy transferred in kilojoules. So we just need to remember that 1 kilojoule is equal to 1,000 joules, which we can then do the conversion. So 32,000 joules times 1 kilojoule per 1,000 joules, right? Because we want to cancel out the joules there. That's what we're aiming for. So that means that I have 32 kilojoules, and that's my solution. So the amount of work done here is 32 kilojoules. Thanks for watching this video. I hope to see you come back.